All right, guys, welcome. I have to take off tomorrow because I got called and they have an opening for me at the MRI facility, which I am desperately in need of. Trying to find out what's going on with my back. So, that's a nice face for me to close on. All right. For some reason, it doesn't seem to want to do both my face and the screen. This is more important. So we'll go ahead and do this. All right. Sorry to those of you who we went over this with yesterday. If you need to, just go ahead and fast forward to where you need to. Okay. So the probability of two or more events can be determined by probability rules. All right. Which rule you use depends on whether or not events are mutually exclusive. Specifically, we're talking about the addition rules, sometimes referred to as OR rules. So these are kind of the same. Actually, they're not kind of. They are the same. Let me try my best to convince you. I want you to keep in mind the Venn diagram sort of perspective when viewing these sets. So we have disjoint sets like this, A and B, right? Or we have non-disjoint sets where there's some sort of overlapping intersection of events like so. So when events A and B are mutually exclusive, the probability that A or B will occur is given as such. Okay, so the probability of A plus the probability of B. Remember, we're going to use this notation for A or B. Okay? Now notice that there's no intersection here. So if they were not mutually exclusive, like we have on the right, maybe we should just state that. Okay, this is mutually exclusive. Oops, I don't know why it gets so bright there. And this is not mutually exclusive. Okay? So if they're not mutually exclusive, what we have to do is we have to take A or B. We add, oops, what happened there? Go back. Huh. I don't know how I did that. All right, anyway, you have to take A, right? You got to add B to it. But when we do that, you might have noticed that, hey, I added something twice. I added this middle area twice. And that's exactly why we have to subtract it one time. So we're not double counting anything. Okay? But notice that I could very well have included this here, right? Remember that this symbol here means and. Okay? But notice, if I'm dealing with mutually exclusive events, what is the value? How many things was the probability of that intersection? Well, there is no intersection, right? That's why this goes to 0. So there's no sense in including it because this is always going to be 0. But there's no need to memorize both. Just use this one. And if it's mutually exclusive, well, this goes to 0. Right? So this is 0 if it's disjoint. And it goes to, something else. Some value, I guess we'll just call it Z, if not disjoint. Right? It's going to depend on the circumstances. Okay, so let's go ahead and take a look at an example. In the United States, let me get rid of this first real quick. There are 59 different species of mammals that are endangered. 75 different species of birds are endangered, 68 species of fish that are endangered. If one animal is selected at random, find the probability that it is either a mammal or a fish. Okay. All right, so let's think about this. 59 different mammals are endangered, 75 species of birds, 68 species, might as well do it in blue as well, 16 species of fish. Okay. Well, clearly, you have to ask her. Let's go ahead and say that A is mammals and B is fish. Now, I don't know. Are birds technically mammals? I don't know. I don't think so. I think they're called avians. But in either case, they're not asking about birds. Focus, please. Right? They're asking about mammals and fish. So, is there an intersection here? Right? What is the probability of A and B? You know what, let's not even think about that. Let's just write the equation. I don't know why this thing doesn't want to do the tap function anymore. Okay, so probability of A or B. I don't know why it keeps getting really bright on me. Sorry about that. Okay, equal to the probability of A plus the probability of B minus the intersection of A and B. Okay. So I'm trying to decide what's going to be the denominator here. I guess we're selecting from all the different endangered animals. So we're going to go ahead and assume that. We're going to say from the endangered pool. Okay, so the probability of A would be 59 out of the total. So that'd be 59 plus 75 plus 68 plus fish, which is 68 out of 59 plus 75 plus 68. And then what is the intersection? Well, there is no intersection, so that's 0, right? So we're going to have, what's that? 117? Yeah, 117 over 59 plus 75 plus 68. All right, it is late for me, but let me try and figure this out for us. So that's 120. It's going to be 134. 134 plus 68 is going to be 194. It's 202. So whatever this is inside a calculator should be your probability. I mean, I might have made a mistake there, but the theory is sound there. Okay? Maybe this one will have an intersection here for us. At a large university, the probability of freshmen takes a statistics class is 0.42. Okay, so I'm going to start writing this stuff down as we go. Okay, so probability, are these all freshmen? Yeah, these are all freshmen. Okay, so probability that it takes statistics is equal to 0.42. All right, probably if it takes intro to psychology, okay, we'll do P for psychology, 0.67. Probably that they take both, the probability that they take S and P is equal to 0.29. Okay, find the probability that family acceptance freshman is taking statistics or intro to psychology. Well, let's just go ahead and follow the formula. Okay, so the probability of S or P is equal to the probability of S plus the probability of P minus the probability of A and, I'm sorry, not A, S and P. So don't bog yourself down too much with trying to get these numbers wrapped around in your head. We'll do some practice with Venn diagrams later on. Okay? Let's throw in these numbers. That's 0.42, 0.67, and 0.29. So that's just going to be some easy arithmetic there for us. Let's see what that. It's going to take five minutes for this thing to load, but I need it anyway. So whenever that thing loads, we'll get the answer for that. Okay. So let's work these examples out. The probability of getting an 8 or a face card. That's just going to be the probability of getting an 8 plus the probability of getting a face card. Why? Because we're going to have to subtract 0 from it. That's, the intersection of 8 and face cards is 0, right? So there's no sense in thinking too much about that. There are 4 8s and there are 12 face cards. So that's going to give me 16 out of 52, which is 8 out of 26, which is 4 out of 13. Okay. Okay, what about an 8 or a heart? Now we're going to have some sort of intersection here, right? So the probability of an 8 or a heart, I'm the worst at drawing hearts. Doesn't mean that I don't have a heart. It means I'm not very good at drawing hearts. Oh, there we go. Okay. It's equal to the probability of getting an 8 plus the probability of getting a heart. And they all look like apples. Okay? Minus probability of an 8 and a heart. There we go. It's a little bit better. That's the key, getting a point at the end. Okay. So we did this already. There's 4 8s. There's 13 hearts. Okay, and there are how many 8s that are hearts? 1. Oops. All right, this is a little bit too serious. There we go. So this will just help us get the answer from earlier. 0.42 plus 0.67 minus 0.29. Okay, that gives us 0.8. Of course, freezes at the most opportune time. Why wouldn't it? All right. So that's going to be 17, 16, 16 out of 52, which is, oh, we just had that, right? Yeah, so it's going to be 4/13 again. All right, I want you guys to do C and D on your own, and we'll compare answers tomorrow. Okay, and that's it. That's all I wanted you to do. All right, we'll come up with the rest of this stuff tomorrow. Maybe I'll throw together a little practice thing for you. All right, so you might want to do that. So finish the notes. Okay, and the practice set if available. All right. All right, guys, that's it. Have a great day. Be safe, and wish me luck. Okay. And let's see if I can figure out how to turn this thing off.